Yes, we welcome you to PSSB, Physical Sciences Silver Bullet. And it's me, Richard. Let us look at, we are still continuing. This is part 2 of this question. So if you have not watched part 1, we would advise you to watch part 1 also, because it's a continuation of that. So we are having the same question. We are having the graph here. The graph is a Maxwell-Boltzmann energy distribution curve. And what do we see here? We are saying the graph X below. This is the graph we are talking about. And it's at 500. And the question comes, the statement says temperature is now reduced to 300 degrees Celsius. And it says, which graph represents this energy distribution? They say choose A or B. Okay, when you look at this scenario, we have a choice to make. The graph at 500 is X, and now temperature is reduced. When temperature reduces, which graph does it adopt? The graph which has adopted is A. Okay, so it's going to be A. Why A? Because reduction of temperature decreases the total energy of the system, or total kinetic energy of the system. So the shift is backwards. You have to remember that as you proceed to the right, kinetic energy increases. You have it here on the x-axis. So when energy is reduced, or when kinetic energy is reduced, the shift is to the left. So we are seeing that graph A, its peak is to the left. So answer is graph A. Why A? That's the reason that the shift of the energy is to the left. Total energy of the system decreases. Thank you. Okay. So that is that. The graph is A because when temperature decreases, the kinetic energy of the system decreases. And this graph A, which represents decrease in kinetic energy. So let us go to the next question. Yeah, and then next question comes. It says, state the effect of decrease in temperature on shaded area. Okay. We said this was the graph at 500, and now the graph at 300 is this one, which is A. Now, from when you trace A, what do we see? What is the effect on the shaded area? The answer is decrease, or it decreases. Okay. So that's the answer. So let us now go to the next question. Okay. Then comes this question 1.33. It says, use the graph to explain the effect of decrease in temperature on the rate of reaction. So how do you answer this one? First of all, we don't know the effect, but you can easily realize it. When you decrease temperature, what happens to the rate of reaction? Like I told you before, temperature is one of the 6 factors affecting the rate of reaction. And the decrease in temperature decreases the rate of reaction. So that one is known. But how do we identify that from the graph? From the graph, how is it shown that when you decrease temperature, the rate of reaction decreases? That one can be identified from the shaded area. Hey, what have we realized? When you decrease temperature, the shaded area decreases. And what does the shaded area represent? It represents number of particles with enough energy to react. So decreasing temperature decreases number of particles with enough energy to react, so decreasing the rate of reaction. Okay. So that is that. Decrease in temperature decreases the rate of reaction, and decrease in temperature decreases the shaded area, as we can see it on the graph. And what does shaded area represent? It represents the number of particles with enough energy to react. So let us go to the next question. Then comes this question 1.4. The statement says catalyst was added to the system, and the question says draw graph X, okay, and indicate the effect of addition of a catalyst. So the question here is, what effect does the catalyst have on this graph or on this system? So generally, what does the catalyst do? It lowers this energy Y, which we call activation energy, and shifts it. Lowering it means that shifting it to the left, and that's the effect. What does it lead to? It leads to increase in the shaded area, and the shaded area represents number of particles with enough energy to react. So addition of a catalyst lowers activation energy, so increases the number of particles with enough energy to react. Let us put that one down. So this is the sketch of our graph X. So how do we indicate the effect of addition of catalyst? We indicate it by shifting this energy here. Remember, it was here. This was the activation energy of non-catalyzed. This is the activation energy of the catalyzed. And what we see here is the additional area to already the area before. So that's how you are supposed to indicate it. Okay. Then comes this question. It says, briefly explain how the addition of catalyst affects the shaded area. Okay, it's apparent here that when you added a catalyst, the activation energy shifted to the left. And what effect does that have on the shaded area? It increases it. So the answer is increase. So that is the answer. The shaded area increases. So let's go to the next question. Yeah, then comes this question 1.43. It says, use collision theory to explain how addition of catalyst affects the rate of reaction. Okay. I have to remind you about collision theory. It says that for the particles to react, they must collide with the right energy and the correct orientation. So what does the catalyst do to the particles? It lowers the activation energy and increases the number of particles with enough energy to react, which increases the frequency of effective collision, which increases the rate. You have to recall that a catalyst is one of the 6 factors affecting the rate of reaction. And when you add it, when a suitable catalyst is added to the reaction, the rate will increase. So let's put that one in writing. So that is that. Addition of a catalyst increases the rate of reaction. That one is known. Catalyst lowers activation energy, which increases the number of particles with enough energy to react. This increases frequency of effective collision, so increasing the rate of reaction. So let us look at the next question. Okay, then comes this question. It says, the statement reads that the system above is closed and it contains 6.0 times 10 power 20 molecules, of which 4.8 times 10 power 20 are having less than energy Y. So the question says, define energy Y. So what is energy Y? This is the energy we are talking about. This one is Y. And what does it stand for? Actually, Y is activation energy. And what is activation energy is the minimum energy required for the reaction to take place. So that is why. So that is that. Y is activation energy, and it is the minimum energy required for the reaction to take place. Okay, so let us look at the next question. Okay, then comes this question 1.5.2. It says, what is the total number of molecules under graph B? Okay, when you look at here, we know that the total number of the system is closed and contain 6.0 times 10 power 20 molecules, of which these ones are below, are having energy below Y. So what is the total number of molecules? Because you have to remember that they said it's closed. Closed means no molecules are entering or leaving. So what does that mean? That means that for each of this graph, the number of molecules, total number of molecules are the same. It's only the energy distribution which changes as temperature changes. So what is the answer? The answer is 6.0 times 10 power 20 molecules. Thank you. So what is okay? So there comes the last question of this setup, 1.5.3. It says calculate the number of moles in the shaded area of graph X. Whatever data we have here is for graph X, but you have to remember that they are looking for number of moles. And how do we get that? Okay, the first thing you have to know is that you need to get the number of molecules in the shaded area. So we'll have total number of molecules in the system minus number of molecules with the energy below Y. What you get out of this one is going to be number of molecules in the shaded area. In the shaded area. So what is the total number of molecules? 6.0 times 10 power 20. What's the number of moles with energy below Y? We have it there. It is 4.8 times 10 power 20. So when you subtract here, what do you get this side? It's going to be 1.2 times 10 power 20. So we have the total number of molecules in the shaded area, this one. But we have to remember that the question is looking for moles. So how do you go about this? We are now going to perform the calculation to get number of moles. You have to remember the relationship between number of molecules and moles. It says N, which represents number of molecules, is equal to number of particles, number of molecules, over Avogadro. And that's what we are going to substitute in to get our number of moles. So this is what we get. To remind you what we did, we have the number of molecules in the shaded area, and then we convert them to moles using the Avogadro law. N is the number of moles, capital N is the number of molecules, and Na is a constant, Avogadro constant. Okay, thanks for your time, thanks for your attention. Don't forget to subscribe. Don't forget to like the video if it has an impact on you.